we're going to look at some famous volcanic eruptions. And we can start off with Yellowstone. We could look also at, we will also be looking at Hawaii. We will look at Mount St. Helens in the Cascade Mountain Range, Pacific Northwest, and we will look at the city of Pompeii and Mount Vesuvius in Italy. So this tectonic plate map is going to provide us some information as to, well, what exactly is taking place. And if you look at the blue, these are divergent boundaries, right? These are the creation of oceanic crust, the magma, as oceanic crust is moving away from each other. And here we have in the red where I have convergent boundaries, and that's just a nice color code. So you can see that in the Pacific Northwest we have Yellowstone that's over a hot spot. We have Hawaii that is a hot spot. Notice this hot spot is different than this hot spot. Hawaii is over oceanic crust, so that when it melts it's going to be very basaltic, whereas Yellowstone is over a continental crust, so when you remelt continental crust that's going to be much more felsic, and it's going to be much stickier, therefore higher viscosity, larger eruption. But notice this Juan de Fuca plate in the Pacific Northwest. The Juan de Fuca plate is still subducting beneath North America, and that is generating this highly volcanic region of the Cascade Mountain Range. And then last but never least, if I look in all of these different tectonic maps, you'll see that, well, there's a lot of activity going on, that there's volcanism all over the earth, and that it should be no surprise to you to find out that not only is the Pacific Ring of Fire a highly volcanic area, but volcanism is very common to Earth. It's constantly recreating and destroying rock, destroying where it's subducting and recreating where we have it diverging. So let's look at this hotspot volcanism map. Everywhere you see these dots, you find hotspots. So hotspot volcanism is not uncommon. It just happens in these little points of locations, and they're not highly populated areas, right? Notice a lot of these hotspots are located with underneath ocean floor. So here goes. Here we go. Hawaiian Islands. These are, as the Pacific plate is moving, it's moving here. It's moving, well, once upon a time ago when the Emperor Seamounts were the volcanic islands, it was moving almost straight north. But recently, the trail of the volcanic islands tells us that it's actually moving very, very much northwest today. And here's a topographic even into a bathymetric map. It shows us the topography. Notice that the big island right now is the highest elevation. That should make sense because that's where the hot spot is under. It's under the big island right now. So the oldest one is Kauai, then Oahu, then Maui, and into the big island of Hawaii. So here's yet another map. It's kind of cool to see these. These would have been really, really large volcanic mountains once upon a time ago, these islands. But they've since eroded over in a couple million years. You'd be surprised at what water can do from precipitation. It erodes down even mountains. So moving on here. And here in Oahu, there was actually a major debris avalanche, a catastrophic landslide that occurred about 2 million years ago. And this would have generated tremendously large tsunamic waves. It would have hit the Pacific, pretty much the Pacific coast, the whole west coast of the United States. So if I look here at the Hawaiian Islands, I'm going to look at this picture for a minute. I've got this mantle plume that's cranking up this really hot rock from the ultramafic source, but as it rises, it cools, it crystallizes out some of the olivine and calcium-rich plagioclase feldspar. And by the time it reaches the Earth's surface, it's all mafic, very low viscosity, very easy for the gases to erupt so they don't build. They come out of the solution. And then notice the further you get from the magma source or from the hotspot, that oceanic crust cools, it becomes denser, and it actually sinks. So what we find underwater are what we call the seamounts. And what we find above water, we call the Hawaiian Islands. And the Hawaiian Islands date to about 7 million years ago, plus or minus 7, 8 million years ago. And so here's a timeline, and these are in millions of years. So the islands get sequentially older the further I get. And they began about 78 to 80 million years ago. And we have a very nice radiometrically dated sequence of the, remember, it's igneous rock, so we can radiometrically date it. Works out very nice. We get a nice timeline of the geology of what's taken place here. Yellowstone. We have the supervolcano. This is a really unique scenario that we have these hotspot beneath continental crust. Continental crust, remember, is granitic. It melts partially, it rises, it's very sticky, it oozes, and because the gases build, when it does erupt, it erupts in mega supervolcano-like fashion, and these are the type of eruptions that alter climate for a period of time. And in this case here, we form a caldera. Once it empties the magma chamber after the eruption's taken place from partial melting, remember, it continues to rise, it can decompress, and as decompression melting takes place, it means it does not need additional heat. Instead of not having heat, it has less pressure on it, so that further drives or amplifies the eruption. And then the caldera forms as the magma chamber is emptied. The rock above the chamber just goes poof, it literally sinks back into it. And that's a caldera. Here's an example of Mount St. Helens that on May 18, 1980, an earthquake of a magnitude 5.0 began a landslide on the north flank. Next, the eruption began. So here's what it looked like. It had literally a landslide from this earthquake. Earthquake moved the land. As it moved, it opened up, it created a weakness in the opening, and that's when the eruption began. And once the eruption began, it literally took this forested area, and look at what it did. It literally wiped them down. They look like toothpicks pointed away from the site of the eruption. And here's what it looks like today. And it still kind of burps and gurgles a little bit. It's like after it ate a 2-pound burrito from Taco Bell. It still has a little bit of gas. And then here's that area that I was mentioning earlier on this lecture slide of the Cascade Mountain Range. There are roughly 13 potentially active volcanoes, and this is the eruptions in the past 4,000 years. Look at Mount St. Helens. It is by far and away the most active volcano within the Cascade Range, and there's a bunch of them. And this is common, or let's just say it's fairly consistent with what we would say is a subductive plate zone. If I go back and look at the Juan de Fuca plate that's subducting here, as it's subducting, I get the basalt that's rising. Excuse me, if I get the felsic material that's rising through here, these are pretty good size eruptions. They're not necessarily planet changers, but they are very significant. So as I look at this, I want to make sure we understand. We might ask, well, how do we know how many eruptions have taken place? And the answer is pretty simple, right? How do we put this timeline to these eruptions, to these volcanoes? Well, one, you look at the volcanic debris fields in and around the volcano. Each layer provides an example of a single eruption. And two, because it's igneous rock, we can radiometrically date the volcanic debris, and this puts a timeline to the igneous rock. So we can even say that there have been these numbers of eruptions. We can even put a timeline to it and specifically say, here's when it occurred. And then last but never least, we have Mount Vesuvius that erupted in Italy, and it buried the city of Pompeii. And these are plaster casts of people who died in 79 AD in the ashfall, in the following pyroclastic flow that buried the city. And so here's my cross-section profile. I know that I have basalt subducting. I have my felsic minerals, felsic even into intermediate. These are going to rise. These are going to be sticky. They're going to really slow the flow of gases that are trying to leave the magma, and they're going to build up. And once it blows, it's going to create this huge ash plume, and it's going to blanket the city. And this city was buried for almost 1,700 years before it was discovered. And they unearthed the city, and there were people literally even found not even hiding like this, people that were actually seated almost as if they were just living through it. They were eating dinner. And so I've seen some really crazy casting photos of it. So to take this back to the original slide, we looked at Yellowstone, we looked at Hawaii, we looked at Mount St. Helens, and we looked at the story of Mount Vesuvius and Pompeii.